Variational inference is a powerful tool in machine learning. It's used to approximate complex probability distributions. This is particularly useful in Bayesian inference. We often encounter situations where calculating the true posterior distribution is intractable. Variational inference offers a way to estimate these complex distributions. At its core, variational inference seeks to find a simpler, more manageable distribution. This distribution, known as the variational distribution, is then used to approximate the true posterior. The goal is to minimize the difference between the variational distribution and the true posterior. Kullback, Leibler, or KL divergence is a common measure of this difference. In the context of image denoising, variational inference plays a crucial role. Noisy images can be seen as clean images corrupted by some noise distribution. We aim to recover the original clean image from this noisy observation. Variational inference provides a framework to model the uncertainty in both the clean image and the noise statistics. By learning the parameters of the variational distribution, we can effectively separate the noise from the underlying clean image. This approach offers several advantages, including the ability to handle different types of noise and provide uncertainty estimates. These uncertainty estimates are valuable for downstream tasks that rely on the denoised images. Yue et al. Proposed a variational inference framework specifically for image denoising. Their approach centers around estimating the posterior distributions of both the clean image and the noise statistics. Instead of directly calculating these complex posteriors, they employ variational inference to approximate them with simpler distributions. A key aspect of their framework is the use of conjugate priors. They model the clean image using a Gaussian distribution. Its mean is parameterized by a deep neural network that takes the noisy image as input. This network effectively learns to map noisy images to representations of clean images. To model the noise statistics, Yue et al. Utilize an inverse gamma distribution as the conjugate prior. This choice allows for tractable inference and captures the uncertainty in the noise level. The parameters of the inverse gamma distribution are also learned during the optimization process. Through end-to-end training, the deep network, along with the parameters of the prior distributions, are jointly optimized. This optimization aims to minimize the difference between the generated images and the ground truth clean images. The framework demonstrates impressive results in removing noise while preserving image details. Generative adversarial networks, or GANs, have revolutionized the field of deep learning. They excel at generating realistic data, particularly images. GANs consist of two neural networks engaged in a min-max game, the generator and the discriminator. The generator network learns to create synthetic data samples from random noise. Its goal is to produce data that closely resembles the real data distribution. The discriminator network, on the other hand, acts as a judge. It learns to distinguish between real data samples and those generated by the generator. This adversarial training process drives both networks to improve. The generator strives to create increasingly realistic samples to fool the discriminator. Conversely, the discriminator becomes more adept at identifying fake samples. This constant competition leads to the generation of high-quality, diverse data samples. GANs have found widespread applications in image processing, including image denoising. Their ability to generate realistic images makes them well suited for restoring images corrupted by noise. By training on paired noisy and clean images, GANs can learn to transform noisy inputs into clean outputs. Early attempts at using GANs for image denoising involved directly applying the GAN framework to the problem. Chen et al. Proposed one of the first GAN-based image denoising methods. Their approach involved training a generator network to map noisy images to clean images. The discriminator network, as in standard GANs, aimed to distinguish between real and generated clean images. While this initial work showed promise, it suffered from limitations. The generated images often lacked fine details and exhibited artifacts. Kim et al. Addressed some of these shortcomings by introducing a perceptual loss function. This loss function encouraged the generator to produce images that were perceptually similar to clean images. The perceptual loss considered features extracted from a pre-trained image classification network. By incorporating this perceptual information, the generator learned to produce more visually appealing and realistic denoised images. However, these early methods still struggled to handle complex noise patterns effectively.